with area because as you guys know, we've already done a lot with area. So let's remember back to Calc AB first semester and really what we've done with area so far. With the X and Y rectangular coordinate system, we have used various shapes. Predominantly, which shape to help us approximate area? Rectangles, yes. So we mostly use rectangles, and we did those in various orientations: left sums, right sums, midpoint sums. We even used trapezoids. We used varying widths of rectangles. But bottom line is, the majority of the time, we've been using rectangles to approximate the area under a curve. That's what we use to figure out the whole Riemann sum thing and definite integrals and all that too. But if we're dealing with polar curves, we've got to do this a little bit differently based on what a polar curve is. So instead of using rectangles, we will use what's called a sector to help approximate the area, establish how to use definite integral to find the exact area. So let's see here. For maybe those of you guys that have forgotten, let me draw a picture of a sector. I'm going to do this as precisely as I can. A sector. How would you describe a sector? Piece of pie, piece of pizza, right? So yeah, it's got two very straight parts and a curvy part. Looks like a piece of pizza or a pie. And so there's a couple of important characteristics to understand about this. The sector is going to have a central angle. So it's going to have a theta right here. And as you guys know, theta can be measured in degrees or radians. And there's, depending on what you're measuring in, there's different approaches. We're going to measure in radians. And we can maybe even talk a little bit about what a radian is and why it's useful, where it comes from if you want to. But yeah, so you get the central angle, and then you've got a radius that is kind of determining the distance from that central angle out there to the curvy part, right? So if you're going to find the area of a sector, and this would be a sector is, maybe I should take a step back. A sector is simply a chunk of a circle, right, where the sector starts at the center of the circle and goes out to the edge of the circle. So if we were going to find the area of a sector, what we would say is area is equal to 1/2 r squared theta. So because a sector is just a small piece of a circle, let me just do a little dotted line here to kind of indicate where the rest of the circle would be. Does that make sense? Circle would look something like that. So yeah, wouldn't it make sense then, couldn't we use this sector area formula to find the area of a circle? If a sector really is just a little part of a circle, we should be able to use it. So let's think this through. If we wanted to get the whole circle, the whole thing, then in radians, what would your central angle be?
For the whole circle?
If we wanted to do the entire circle.
2 pi.
2 pi, wouldn't that be the central angle? You go all the way around? So for maybe don't write this down unless you really want to. So for the whole circle, the area would be 1/2 r squared times the central angle of 2 pi. And look what happens. Wouldn't the 1/2 and the 2 just cancel out really nicely? You'd get r squared pi, or the more conventional version, pi r squared.
That's so cool.
Do you get it? And so that's a way of thinking about the whole area of a sector. What are you guys doing with your calculators? You're bugging the heck out of me. What?
Nothing.
Okay. 2 plus 2. Yeah, like every time I look over here, you're like, check it out, check it out, check it out. Hee 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 hee. Let's just stop the whatever that is.
So that's the area of a sector, that equation, right?
They both are, yeah. And so what I'm saying down here at the bottom is, what if we wanted our sector to be the whole circle? I just wanted to make a connection.
Just like the general sector.
Yep, this would just be the area of a sector. So if we had, so here's just a basic example of what if we had a sector that wasn't the whole circle. Like what if we had that little piece of pizza right there, and what if we knew that the radius was 3 and the central angle, I don't know, let's say it's pi over 4 roughly. If it were that, then we'd say area is equal to 1/2 times 3 squared times pi over 4. And so that would be 9 pi over 8. So the whole, just the sector there would be 9 pi over 8. So this just allows you to find areas of various fractions of the circle, if that makes sense. Make sense?
Yep.
Okay, cool. Okay, so did you guys do anything with sectors in like pre-calc or anything?
We did a little bit.
Did we do that basic glue equation?
Yeah.
I think that's all we did.
And of course you can take that and you can plug a jug, right? You get an RE theta, you plug it in.
Right, that's
Area of a
not.
sector. Yeah, okay. So that's the area of a sector. And then, so let me build this out like this. So let's say we had, I don't know, let's go with the classic cardioid. So let's say we had a cardioid that looked a little lopsided, but I'm just going to leave it. Say we had a cardioid that looked like that, and let's say that we were going to try to find the area of that cardioid, the whole thing, let's say. Let's say we had absolutely no idea how to find this. Couldn't we, like, if you think back to area under a curve, if I would have had you try to find the area under a curve, you might have eventually arrived at, hey, what if we just use some rectangles? That would be a good approximation, right? So same thing here. I mean, it's a bigger stretch to say, hey, let's use some sectors, but maybe you'd get there, right? So what if you said, let's find this area, and you said, let's start using sectors. Couldn't a representative sector maybe look like we could just go here, and you'd have like a little bit of extra, and there, and you could have another sector here, and maybe that would be, oops, something like this, and then you could come all the way out here. You have another little sector like that. Do you see how I'm kind of building up this area little by little? And so these sectors, you can see that kind of like the rectangles with the rectangular graphs, these sectors are going to be like an okay approximation, but you can see little gaps or some overlaps, and as good as it might be, it's always going to be just a little bit too much or a little bit too little. It's going to be an approximation. So the concept that I'd want you to arrive at is at the very bottom of my screen. It comes next. So the way that we'd actually find the area precisely is, wouldn't we have to take the sector itself and take those two radial lines that kind of define the sector and squeeze them down to where the sector is like super skinny? And if the sector got really, really, really skinny, then wouldn't we need a lot of sectors to fill the whole shape? What are we talking about? An infinite summation, also known as a definite integral, right? And so then when you look at the formulas that are coming up here, you can see that, of course, they involve a definite integral. And so if we are going to do this, we would say, you can see that sector area formula in here. It's 1/2 times r squared times a little itty bitty change in the angle, right? And so it really is just 1/2 r squared theta. And we're going to just add up a ton of little tiny skinny ones, ton also known as going towards infinity. The only really to do that was with a definite integral. Yeah.
Are we talking about r as in radius or r as in the equation of theta?
So this goes back to what a polar graph is. So yes and yes.
Okay.
So the way that a polar graph works, of course, is that the distance from the origin out to the graph itself varies as theta changes.
Okay.
So as theta goes from, say, 0 to 2 pi or something like that, then the radius is going to go from long to short to long to short, whatever it happens to be. And so when I have that r in there, that is a radius, and it typically will be in terms of theta, which is what I've got right there, right?
Yeah.
So r is equal to f of
Okay.
theta. So that'll be like the
Gotcha.
r equals blah, blah, blah theta equation that would determine the polar graph itself. And then I suppose let's talk about the alpha and the beta that's right there. So if we come down to here, let me just do a different graph. So let's say let's do like maybe like a rose. So let's say I think we did a rose like this before, where it did come down here towards the bottom, and then did that, and then did that. So let's say that we wanted to find, and we'll do something really similar to this, if not this exact same thing here in a second. If I wanted to find the area, say, of just one or even just like say part of the petal of the rose there. So let's say, and I don't know why exactly we'd want this, but let's just do it for instance. Let's say that I wanted to know the area swept out right there. Let's just say that purple area. So then what you do is, you know, that rose is determined by some polar equation, and that polar equation would be something like r equals f of theta. As you can see, and Darian, this kind of goes to your question earlier, as theta sweeps out 0 to pi, you're going to get this varying radius length from 0 out there to 3 and all the stuff in between. It's going to give you this rose. But then as far as how do you set your limits of integration, you guys all saw up there, area is equal to 1/2 times the integral from alpha to beta of f of theta squared. So what are the alpha and the beta? And this is maybe the last piece that we need to put in here. With the rectangular stuff we've done so much with, didn't we accumulate rectangles from left to right? You know, we'd say, you know, say you had, oh, I guess I'll just erase this. Let's say you had, you know, this would be something really, really old. Let's say you had like integral from 2 to 7 of f of x dx. Isn't that basically saying, hey, let's accumulate all these rectangles starting at x equals 2 and stopping at x equals 7 as we like accumulate from left to right? With polar, like left to right doesn't really make a lot of sense, does it? Because we're not using rectangles, we're using sectors. So what would you guess the alpha and the beta would be?
0 and 3.
0 and 3, why 0 and 3?
Just a guess.
But what are the 0 and the 3?
The origin and the farthest petal.
So what's he referring to when he says 0 and 3? The lowest and the highest what? I don't think so. Well, so he's saying, let's focus on the 0 to 3 for just a second here. So 0 to 3, based on the picture, would have to be the radius. Yeah, the radius goes from 0 to 3. And while that's a valid thing, I would point out that your variable is theta,
Oh, yeah.
right? So it doesn't really go that well with r. Sean said something about 0 and pi. And what are 0 and pi?
Angles.
Those are angles, I agree. And so the alpha and the beta are definitely angles. For the example that I've drawn up there, I don't know that I would say 0 and pi, because wouldn't 0 and pi give you the entire rose area? You would sweep out all of it if you did that. You'd be covering that petal, that whole petal, and that whole petal if you swept all the way from 0 to pi. So, you know, for the example that I have right there, I don't know exactly what those angles are, but maybe it would be pi over 6 to, I don't know, pi over 4 or something like that. That's an estimate, but do you get the idea? You'd sweep out. So you're basically going to ask yourself, at what angle does my area start? Like, where do I start caring about the area? And then at what angle do I stop caring about the area? Make sense? So, for example, let's go back to Sean's idea. If, with this one, if I did want to find the whole area, and this is where, you know, your basic knowledge about roses and polar graphs and such would be very helpful. If I did want to find the whole area, I would say area equals 1/2 from 0 to pi of, let's see here, whatever that is, I'm just going to call it f of theta. We know it's going to be like, what, I think it'd be sine of 3 theta. So yeah, sine of 3, or 3 sine of 3 theta. Times d theta. Does that make sense?
Is it squared, right?
Oh, squared, sorry. Yep, I forgot my squared. I was so busy thinking about exactly what the equation would be, I forgot the squared. You're right. Okay. So have I filled that out enough? The idea here would be that you're not just looking at the formulas you see on your page, you're like, oh, cool, another formula to memorize. I want to try to have you have a sense of like where it comes from, why it is, what it is, what's the radius doing, what's the theta doing, why does it have to be alpha and beta instead of A and B, and all those kinds of things. Yes, ma'am.
So you did 0 to pi because it's odd amount.
Right, yeah, so that's why I said like our basic knowledge about roses specifically, we know that because it's, you know, it's an odd petaled rose, we know it's going to be, there's 3 petals, we know it's going to be 3 theta, and if I remember right, this would be sine of 3 theta, and because the max length of the petal is 3, I think it would be 3 sine of 3 theta. Does that make sense?
Okay.
And so I take all the way back to say, if the coefficient on the input is odd, then you only need 0 to pi to get the whole rows.
Okay.
Make sense?
Mhm.
Okay.
If
Oh.
it was like 4 pi, you would do 0 to 2 pi.
Any other questions? I don't want to rush. We don't have to rush. Anything seems amiss? No, we're good? Okay. Well, like I said, I don't remember. I think this next example might be pretty darn close to the one I just sort of made up. I hope it's not exactly the same. If it is, it's pretty close. We'll survive. So we're going to get creative with this one. So I would say let's do a couple things preliminarily with this. Number one, get your calculators out, go to polar mode, and let's graph this. Just kind of get a sense of what it looks like. The instructions say find the area of one petal of the rose, given by r equals 3 cosine 3 theta. And like I said, we're going to get creative with this, and there is a purpose to that creativity. And you are welcome to be as creative as you want with this as well. But first off, just start by graphing it. R is 3, so I think this one has got to point that away. Oh, so close. Hey, that's one of my better roses. I'm going to zoom out and it'll look even better. Okay, cool. So we agree that's it? Okay, so this is where we get creative. And I think that there are lots of ways to do this. In fact, it could be said there are infinitely many ways you could do this. We just want to be flexible and be able to understand what's actually happening here. So it just says find the area of one petal of the rose. So I'd like to hear from you guys some strategies. Like, what do you think, just kind of a broad plan of attack to find this? What could you do? What do you think, Darren?
I would
Sorry.
say, take it from the point where it's, you could find the whole thing and then divide it through by 3.
That's a classic way of doing it, right? So you could just say, hey, let's find the whole area and then divide it by 3. You can see the symmetry. There's 3 petals. That's a classic way of doing it. So we can investigate that for sure. Blake.
We go from pi over 2 to pi for our limits.
So from pi over 2 to pi,
Oh, wait, no.
so that would be a distance.
From pi over 2
0
to 3 pi over.
Pi over 2 to 3 pi over 2. So that's when.
So that would be a distance of pi.
Yeah.
What would that give you if you did that?
The whole thing.
They give you the whole thing, and then we'd have to divide by 3.
So we go pi over.
Say again?
0 to pi over 3.
0 to pi over 3. So why is 0 to pi over 3?
Because if pi is the whole thing, and there's 3 petals, then you just divide it by 3.
You think, yeah, if you divide the domain by 3, then sure. Yep. I think that makes sense as well. Other thoughts? These are a couple of real good ideas. I think they'd all work. There are other ones that are. So pi over 2, let's think about what pi over 2 to pi would be. So pi over 2 to pi, that's a distance of pi over 2. And so we know that to get the whole rows, we have to go a distance of pi, right? Or a domain of pi. That's pi over 2. So if we did do pi over 2 to pi, wouldn't we get essentially half of the area of the whole thing? Which, you could then take that and figure out what fraction you need to multiply by to get the third of the whole thing, right? So that would work. It would just be more and more fractions. It would eventually work, yeah. You just have to pay a real close attention as to like what that actually means and then work with it from there.
Go
Yep.
pi over 3 to 2 pi over 3.
Yep, well, that's a distance of pi over 3. Yep, that would work too, for sure.
Pi over 3 to pi.
Some of these, so I would say,
Pi.
basically, as long as the domain between the angles is pi over 3,
We
you
go
know,
4 pi over 3 to 5 pi.
yeah, well, you could do like 29 pi over 3 to 30 pi over 3.
Pi over
And
3 to 2 pi.
do you get what I'm saying? Do you see why there's an infinite number of ways you could do this?
23 pi over 3.
I think, though, like if you think about this, let's go back to the one suggestion where you guys said, hey, let's do 0 to pi over 3, which I think makes perfect sense. And numerically, it should, I think, work out pretty well for us. Let's think about what that looks like graphically. It's a little weird. Here's what happens. So if we started off facing 0 to pi over 3, or started off facing 0, that's 0, isn't it? 0 radians. And we're headed towards pi over 3. Well, as we start sweeping out area, we'd start sweeping out like these little itty bitty sectors. And we're not to, do you see what I'm trying to do there? We're not to pi over 3 yet.
It's pi over
So as I start getting pointed about in this direction right here, I'm not going to be on that pedal anymore. Where would I be as I continue to rotate?
bottom.
Ended up down here, wouldn't I?
Yeah.
And so like right about there, I would stop. That's pi over 3-ish, something like that. But that whole time that I went from whatever that dotted line angle was up to pi over 3, wasn't I going backwards onto that other pedal? And the good news is you're getting negative radii, right? So you might get concerned and say, well, wait a minute, wouldn't that second half be negative radii, and wouldn't they cancel out and eventually give us 0? The answer is no. Do you know why?
Because you can't get negative area.
Well, sure.
Coordinates, so there are no negatives.
Oh, no, you can have a negative radius with polar. In fact, in fact, let's test this out. So if I said r equals 3 cosine of 3, and I went ahead and plugged in that pi over 3, right? It would be the very end of the integral. Well, you'd get 3 cosine of pi, and 3 cosine of pi is negative 3, which is why we're ending up in the third quadrant in the first place. So why wouldn't these areas effectively cancel out and you'd end up with this 0? Because they wouldn't. This would still work. Why wouldn't it end up being 0?
The square.
The squared, right? Remember the formula is 1/2 integral of r squared d theta. And so whatever that radius is, whether it's a positive or a negative, it's going to get squared and it'll accumulate as a positive because of the being squared part. Does that make sense? Okay, awesome. Let me do a little erasing here. So do you see how the 0 to pi over 3 I think is going to work just fine, but do you see how it's just a little on the awkward side because we're getting like half of a pedal plus another half of another pedal? So can you guys think about what could we do to get just more of a classic, like let's just get one pedal and call it good. Like let's, instead of getting half of one and half another, how could we set it up to where, and by the way, all these will work. And I'll explain why I'm trying to get creative with this, but how could we just essentially encompass one pedal and not bother with the whole half of one, half the other, or some fraction of one, fraction of another?
So just get one pedal.
How could we just basically set our limits so that you're just getting one whole pedal without having to get fractions of 2 of them?
Negative pi over 6 to pi over 6.
There it is. Okay, so let's talk about that. So if we did integral from negative pi over 6 to pi over 6 of, 3 cosine 3 theta squared d theta, this would actually do it. I'm wondering, Alyssa, where did you come up with those numbers, the negative pi over 6 to pi over 6?
Well, we integrated from like 0 to pi over 3, we got half of the first one and like half of the one of the bottom left. And so the top half is to pi over 6 and the bottom half is symmetric.
And the symmetry tells you that, right? Like half of pi over 3 is pi over 6, right? No, you're using really good logic there. I agree. If somebody said, hey, Alyssa, that's really neat logic and everything, but can you show me with math? What could you do? I'm asking everyone this. I'm not just putting Alyssa on the spot. She's right. It's negative pi over 6 to pi over 6. She's totally right. And her reasoning is sound. She's like, hey, I saw the pi over 3 thing, cut it in half, blah, blah, blah. Makes great sense, right? So she's basically talking about negative pi over 6 to pi over 6 for the alpha and the beta. And you see how you'd sweep out just the single pedal? And so my question is, mathematically, how do you...
It's positive.
Say again?
Cosine is positive in those regions, like when pi over 6 and negative pi over 6, the value would be positive.
Sure. And you got a positive radii. Okay, but again, like, how do you know that it's exactly pi over 6? How do you know it's not like pi over 7? Beyond the, hey, half of pi over 3 is pi over 6. You know what I mean?
Could you just plug it in?
Plug what into what?
Plug
Pi over 6 to R.
You're gonna get 0.
Oh, okay, now we're starting to talk, right? So if you plugged pi over 6 into theta, you'd get r equals 0. That feels a little guess and check-ish. How could you go the other way? And
0 equals.
there you go, 0 equals. So here's how you could do this. You could say that essentially aren't the pedals in a rows like this, aren't they defined by a 0 radius? Like a new pedal starts every time r is 0. So if I said 0 equals 3 cosine of 3 theta then I could solve that equation, and I'd be willing to bet that if we solved it correctly, we'd get a bunch of nice angles like negative pi over 6, pi over 6, and then so on and so forth, right? So it would be pi over 2 after that, et cetera, et cetera, et cetera. You just keep essentially adding pi over 3 to get to the next one, right? You guys with me? Does that make sense? So that would be a good strategy here. And it's not always going to be a universal strategy, but because the rows starts and stops, each petal starts and stops at the origin, setting r equal to 0 would be a way to define each petal. We still haven't even found the answer yet, but let's kind of summarize all the stuff we have found as far as what might work. So Alyssa's idea would work. One of the original ones was 0 to pi of 3 cosine of 3 theta quantity squared d theta, but then take that and divide it by 3. That was a good one. And then we had the, let's just do
Wouldn't that be 1/6?
oh, sorry,
It's already 1/2.
I forgot my 1/2. Let's just do that. There we go. So 1/2, 0 to pi over 3, radius squared. I mean, these three were all, you don't have to write all these down unless you want to. Totally fine. Those are three, and there was others, of course, as far as examples of things you could do. And really, the honest truth is you could make your limits of integration whatever you want them to be, as long as you understood how they related to a petal of the rows, then you could then transform it into whatever you want. So let's talk about why we would go through this whole exercise of like, hey, let's figure out like 17 different ways to find the area of one petal. In the case of a multiple choice, you're going to have to think this way. Think about it. Just like there have been many, many questions over the year and over last year as well, where it'll say, hey, set up an integral expression for blah, blah, blah. Well, in the past, like with rectangular area, if it said which of the following integrals would be equal to the area under the curve, there was kind of like one integral, and the limits kind of had to be what they had to be, and that was just it. Not so with polar, right? The limits could be an infinite number of things, and we're not going to get crazy. You know, it's not going to be like, hey, 101 thirds pi to 102 thirds pi, or just something ridiculous like that. It's going to be all kept within the typical domain of one of these things, but you never know. Like, what if one of the options is this negative pi over 6 to pi over 6? I'd want you to recognize that, oh yeah, maybe that's the one. Or what if they define the angles to get this one in the second quadrant? I'd want you to recognize, well, hey, that's still valid. It's finding a different petal than maybe I would have found, but being able to match up an integral expression with what would be the area of something like this. Does that make sense? Okay. So what I would like for you to do now is pick one of those, whatever one you want to pick, and let's figure out what the area actually is. Maybe you've already done some work with that. Let's see here. With your calculator, yeah, unless we want to do, you guys want to do some trig substitution? You're like, no, okay. Well, you could, because you'd get cosine, right? You'd get 9 cosine squared of 3 theta. So you'd have to, anyway, you have to use a half angle. We didn't even do the half angle identity versions, did we? So you guys are off the hook. Darn it, you're totally off the hook. Okay, yeah, so set it up, use your calculator, figure it out.
Yeah, 2.3562.
2.356.
No, you forgot the divide by 1/2.
The 1/2 maybe? Did you get 4.7 or something? Yeah. 2.3562. Okay. So you guys agree with that number? I heard that several times. Okay. So big takeaways are this. The angles for your limits are very important, but they could be lots of different things and still be right. So it's possible I could take the 9 of you plus McKenna plus myself, and we could do some question like this, and we could have 11 different answers, and they would all be correct potentially, right? As long as the stuff we did actually makes sense. Yeah. I can just see Blake being like, hey, 101 million pi over 3. Yeah, I get it. There's lots of stuff, and you could be a pain or not, and it's okay if you are. But the idea here is that there's lots of options. Another big takeaway would be that we are not accumulating area from left to right or from right to left. We are sweeping out area as a radial line kind of sweeps across a graph like this, right? Is the radial line goes from 0 to pi, or in this case, negative pi over 6 to pi over 6, or whatever. It's sweeping out area. Does that wording go okay with you? Sweep out area, kind of like a radar. You know, like you ever seen the old school radar that actually pivots around a center point? So you're just sweeping out area as theta changes from whatever to whatever.
It's funny to think though that since the domain of that is this pi,
Mm-hmm.
but if you go in the same time,
You get twice as much area.
okay.
Yeah. Yeah, so if you did, I bet you, I mean, we could do this if you want. If you did, 1/2 integral from 0 to pi, you'd get all 3 petals. If you did 1/2 integral from 0 to 2 pi, you would get all 3 petals and then all 3 petals again. So you'd get twice as big of an area as you should. Yeah, okay. You guys have any questions about what we're doing here? Hope this is making sense. I think it's a pretty good transition from rectangular to polar when it comes to area. Same concept, just sectors instead of rectangles. And it'll work?
Yes.
Yeah. Okay, cool. All right, well then, let's move on to our other example. We definitely won't do more than this one. Let's do this one right here. Check out example number 2. That's about right. Okay, so again, like we did with example number 1, if you guys would, take this and graph it. This is 2 graphs now. This will be something different. It's a typo. So it says circle, and I think this is the best way to go here. I'm sorry. Thank you for your forgiveness. So it should be r equals 3 sine theta. So this should be a circle now. I have a sneaking suspicion that's a typo left over from a previous year, and I still failed to fix it. Okay, so it's a circle now, right?
Yeah.
Okay, good. It should be a circle above the x-axis, like entirely above the x-axis, except for the origin.
Minus
So you find,
Quite a lot.
wait, so you find the area of the overlap?
So it says, yeah, the area both inside the circle and inside the cardioid. So there will be like a certain region that's inside both.
Yep.
So let's see here. So the circle, it's going to be hard to draw. Does that make sense? So you know what? I'm going to try to be really smart about this. Hang on.
Let's go through your window. It's not perfectly circle.
I mean, my window is perfect squares.
I have a question. What's the answer?
That and Peter cut is
You have a question? What's the answer?
Yeah.
Honestly, don't know.
You're gonna do it.
You know what? I'm going to get smart here.
dimpled something.
Oh.
Because if you subtract,
No, it says
If you
cardioid.
subtract-
if you subtract, you're gonna take way too much.
Yeah, yeah, so that is something. But subtract the other direction, add that much back in. See, that's what I was saying. Oh. Because if you subtracted like
I'm still trying
the
to subtract,
circle,
and I think
if
it
you put a
works.
circle and then subtracted the little one, you would have 2 little ones, and then you put the other one and subtract.
Okay, there's my attempt at a circle. I know it's a little elliptical. Are you okay with that?
Yeah.
Okay.
Take
And then the cardioid. The cardioid it's like this, right? It kind of comes down. That's terrible. And it goes up to 2, doesn't it? So
There you go.
pretty good?
Yeah, good job.
Okay, thanks. Sometimes these are a challenge. It's still lopsided, but we're going to pretend. At least I am. I'll appreciate it if you pretend to.
I'll do my best.
I know. Okay, so we have the graph settled. We got the typo over and done with. Let me fix that again. Okay, so
They're both on. That's just one thing.
So guys, with something like this, there's going to be a real temptation to just be like, hey, let's find the area of the circle and the area of the cardioid and subtract.
Wrong.
Doesn't work quite like
Ah,
that.
so close.
Because that's a very rectangular way of thinking about it, right? You're basically saying integral of high minus low. And there's not really high minus low. There's just like near and far, kind of. But here's the thing I want you to think about. Remember one of the big takeaways from that last question is that when we are doing area with polar graphs, we are sweeping it out from such and such an angle to such and such an angle, right? We're sweeping it out. So maybe the first thing we ought to do here, I'll erase this in a second. Let's make sure we've clearly defined the area that we're talking about. Aren't we talking about this area that I'm trying to highlight here?
Yeah.
Yes.
So the two little loops down below, not it. And then the bigger part of the circle kind of up above, also not it. So it's just that purple part. So I guess what I would encourage you guys to think about, like I said, is that we are sweeping out area from whatever angle to whatever angle, whatever's appropriate. We okay with we're not going to be subtracting high minus low? Okay. So here's what I would try to help you visualize. The first angle I'd think about is, what if we were facing straight right? So what if you're facing this way? Is that angle to the right? Sorry, that's not a very good color. Is that going to be part of our region if we were facing straight right?
No.
I would say actually probably yes. Because when we are facing straight right, this would be like the beginning of the area, wouldn't it? When you're facing straight right, what's the radius of the circle? 0. Yeah, when you're facing straight right, the radius of the circle is 0. And then as you started to sweep out, and I'm going way too far here, but as you started to sweep out kind of like counterclockwise, wouldn't you start picking up this part of the circle? It's a really tiny little sliver, but it would be that little red part before you hit the intersection of the blue and the red. Okay. And so the concept here is, as we sweep out the area, we're going to get these little radial lines defining these little tiny sectors up to about that point. And and we haven't figured out the angles yet other than the 0. So between 0 and whatever that angle is, we're going to be using the circle to determine how long the radius is. Then, once you get to that intersection point and move beyond it, well, now these radial lines are going to be determined by the cardioid out there, right? And so once you get to that intersection point, you continue to sweep out counterclockwise. Then now the circle is not going to be the thing that's telling the radius how long to be. It's going to be the cardioid. So instead of a something minus something, do you see how this is really going to be a something plus something? It's going to be like this little itty chunk of area determined by the circle, and then a much larger chunk of area determined by the cardioid, and then more cardioid, and then a little tiny bit of circle. So as we come up to here, the cardioid is still telling the radius how long to be. And then once I get to this intersection point, now that little chunk that I haven't filled in yet, and I'll fill it in right now, isn't this determined by the circle? It's a really pretty picture. Surprised you guys haven't made a comment about how nice it is. Thank you. Yes. It is kind of, yeah. Beautiful picture aside, does that concept make sense?
Yes.
Okay. So we're going to make the little seashell disappear.
No.
Sorry. Maybe it'll come back. Did I just take away your dreams? I'm sorry. I'll try to bring them back.
My rose.
Your rose. I already took away the rose. Now no more seashell.
Seriously.
That's pretty close to your dreams.
No, you're right. That's all I want in mine.
Roses and seashells. That would not be a bad life.
It'd be pretty good.
Yeah, I think it'd be okay. All right. So what I'm going to attempt to do here first, we're going to make the seashell sort of come back. I am going to code the area determined by the circle, we're going to do in red. So I'm going to say, what if I had a radial line that started facing straight out to the right at 0, and then I started to sweep out these little radii and eventually got up there to that point of intersection? Wouldn't it be that little itty bitty sliver there you can see? The whole time the radius is determined by the circle. So I'm going to say that area is going to be 1/2 of the integral from 0 to what? Whatever angle determines the intersection point. How do you think we could find that?
Set them equal to each other?
Set the two radii equal to each other? That's exactly right, because where the radii are equal is where those two curves would intersect. So I'll do this real quick and then I'll erase it. Maybe I'll just leave it over here. So we would say 3 sine of theta is equal to 1 plus sine of theta. So if we subtract over, I'd get 2 sine of theta equals 1. Sine of theta is equal to 1/2. And now your crazy awesome skills, your unit circle skills, what's theta have to be? Pi over 6. That's right. So that intersection point would be when theta is pi over 6. So we could say 1/2 the integral from 0 to pi over 6. We want to be super careful that we get the right radius in there. So the circle is the thing telling the radius how long to be. And so it's going to be 3 sine theta quantity squared for this radius. Yes, sir?
We haven't gotten there yet, but if we were looking at this, could we just cancel out the 1/2 and say we're doing
Use symmetry?
Yeah.
We're going to
that's
do
the
that.
best way to-
That's exactly what we're going to do. You have a great idea. This is going to finish pretty quick here. So then you all get the little tiny sliver there in red determined by the circle. Once we get to that intersection point, which is when theta is pi over 6, then we're going to have to switch over to the cardioid telling the radius how long to be. And so that would be all these little guys right here. The radius is obviously getting a little bit longer each time. And kind of in accordance with what Darian suggested, I'm going to stop my little graphic right about there. Because isn't that a nice point of symmetry for this graph? And so I'll stop right there. And of course, that's a pretty easy angle to find. That's another good reason to do this. What's that angle?
Pi over 2.
Pi over 2. Good. So I'm going to add to this plus 1/2 the integral from pi over 6 to pi over 2. And that'll cover the blue area. I'm trying to color code this as best I can. And now when it comes time for the radius squared to go in there, we're not going to use the circle anymore because the circle didn't have anything to do with how long that radius is. It's all about the cardioid. And so this would be 1 plus, is it 1 plus sine theta? It's off my screen. Okay. Squared d theta. So to bring it all the way back around to what Darian suggested, this of course is only half of the full area. And this is a pretty nice place to stop because all we really have to do is either erase the 1/2 or just put 2 times that whole thing, and that would end up giving us the entire polar area. And I don't know if you guys have had a moment to try to run this through the calculator, which is what we would do if we were going to take it all the way to an answer, but evaluating that integral would do it. I don't know if you've got about 20 seconds before the official end of class, if anybody's fast enough. 3.927?
Yeah.
All right, well, I don't know if we'll get a confirmation on that or not, but you are usually on the money, so.
3.927. Well, it's 92699.
Okay, I'd say that one.
I figured it was appropriate around.
Okay, so I hope that's the right answer. I'm guessing, seems reasonable, so whatever. Hey,